All right, so I ride my bike a lot, and I just wanted to show you the effects of air resistance. So here's a bike ride. So this is the distance in miles, and this is the speed. So you can see on this day, and I usually go, out and back, right? So here, the speed didn't change much, right? And so this was a day where there's not much wind at all. Doesn't happen very often here, but boy, when it does, you love it. I like it anyway, most people don't. Now look at this though. So this is, so here, here I was going with the wind, and here I was going against the wind. And you can see it's incredible, right? It's pretty obvious, right? And here I'm going pretty, at a decent speed, and then I slow down a lot, right? So that just shows you the effect of wind, Okay, here is a wonderful question which is going to use, this is like a review, so I think it's worthwhile. It's one of these relative motion problems. Okay, relative motion. Okay, a steady wind of 10 miles an hour, that's not very much, is blowing from Laie to Haleiwa. A Laie cyclist pedals to Haleiwa averaging 18 miles an hour, because the wind is with the cyclist. On the way back to Laie, the cyclist struggles to maintain a speed of 14 miles an hour against the wind. And all these speeds are relative to the ground. What is the velocity of the wind relative to the cyclist on the way to Haleiwa? Okay? So, because remember, with that drag speed, this is the speed of the air relative to the object, right? And so, if we want to use this equation, we've got to figure out the speed of the wind relative to the cyclist, right? Okay, so number one, but hold it, so let's say here's Laie, and here's Haleiwa. All right. Okay, so for number one, we're going from Laie to Haleiwa. And let's just use Randy Knight coordinates, all right? So that's plus direction, okay? And so the wind is blowing from Laie to Haleiwa. So the velocity of the wind relative to the ground is in that direction, right? That's what it says. Okay, let's use that funny formula that we learned a long time ago. So we want the velocity of the wind relative to the cyclist. So let's do it. Okay, wind, cyclist, ground, ground. Hope you remember that silly little formula. Okay? All right. So, what's the velocity of the wind relative to the ground? We're going from Laie to Haleiwa, 10 miles an hour. 10 miles per hour. Now here's the important thing. What's the velocity of the ground relative to the cyclist? What? Remember we talked about that. Well, remember, the velocity of the ground relative to the cyclist equals minus the velocity of the cyclist relative to the ground, right? We talked about that before. Okay, so the velocity of the cyclist relative to the ground is 18 miles an hour, right? So that means that the velocity of the ground relative to the cyclist is minus 18 miles an hour. Okay. Don't forget that, all right? So therefore, what's the velocity of the wind relative to the cyclist? 10 minus 18, minus 8 miles per hour. And that makes good sense, right? Because think about it. If the wind is blowing 10, but you're going 18, aren't you plowing through the air? Yeah, you're plowing through the air. The air is, moving against you. Okay? Think of air as jello if you want to, If the jello is going 10 and you're going 18, you're plowing through that jello. It's a drag force, Okay. All right, now number two. What's the velocity of the wind relative to the cyclist on the way back? Okay, so now, here's Laie, here's Haleiwa. Now we're going back, right? Okay, so the velocity, velocity of the wind relative to the cyclist. Same equation, right? Same equation. Okay, same equation. Okay, so what's the velocity of the wind relative to the ground? It's still 10 that way, right? The plus that way, so it's still 10. Okay, now, what is the velocity of the ground relative to the cyclist? Well, remember, velocity of the ground relative to the cyclist equals minus velocity of the cyclist relative to the ground, right? Now, what's the velocity of the cyclist relative to the ground when he's coming back? 14 miles an hour. So we want minus 14 miles an hour. Wait. I'm sorry, I screwed that up. What's the velocity of the cyclist relative to the ground coming that way? Yeah, minus 14, right? Because it's coming this way, that's the negative direction. So velocity, cyclist relative to the ground is minus 14. But we want minus that, so it's minus minus what's plus. So it's plus 14 miles per hour. And what's that? 24. Okay. Now, but wait a second. Remember, the cyclist is going this direction, right? The wind, this is a positive, so the wind is going this direction. No kidding. I mean, right? But what I'm saying is, to the cyclist, the wind is going 24 miles an hour, right? The cyclist is going this way. It seems to the cyclist that the wind is going 24 miles an hour that way. Now, so let's look. So this is 3 times this magnitude, right? Right? This is 3 times that magnitude, agreed? But the drag, look at the equation, the drag is proportional to v squared, right? The drag is proportional to v squared. So this is 3 times that, right? So what's the drag coming home compared to the drag going out? Well, if it's v squared, and this is 3 times that, the drag is 9 times. 9 times, okay? So in other words, the drag here coming home to Lidia is 9 times the drag going up to Haleiwa. And that's why, that's why the guy was going 18 out, but only barely going 14 on the way back, because the drag is 9 times larger coming home. Okay? So that's kind of a cool example. It's a nice review problem for you. All right, yeah. Okay, now we are ready to do a kinematics problem. So we have to do the pictorial representation, that whole bit, and we're going to realize that we need acceleration, so we're going to have to do the force diagram to get the acceleration. Wow, so this is going to be everything that we've learned, like I said. All right, and this, again, these are just the steps. You've already seen this. All right, choose a coordinate system, resolve the vectors, and see if it's an equilibrium or not equilibrium, and then you already know that. Okay? All right, so this is an easy one. It's going to get much more difficult. So everybody read that, please. Think about it. All right. A skier slides down a hill, frictionless, oh my gosh, crazy, frictionless ease, what's speed at the bottom? So, I mean, you read that, and you say, okay, she's going like that, and we want to know the speed at the bottom. It's kinematics, right? Kinematics, piece of cake, So, let's just do it. So, let's draw a little motion diagram, just to have our brains work a little bit nicer, right? So here's the start, here's the end, right? And acceleration is that way, right? All right, that's cool. how many points do we need for our pictorial representation? Just 2, right? Just 2, right? So, well, let's kind of kill 2 birds with 1 stone, right? Because notice, they don't give us the distance from the start to the end. They just tell us the height. Kind of pain, right? But anyway, so let's just do this. Whatever. Okay. So this is our first point. So that's x. Okay, we're going to be super lazy. We're going to do this in a 1-dimensional problem, not a 2-dimensional problem. Because we can, why not? We're just going to tilt our axis. Right? So this is going to be our x-axis. Is all we need. Totally smart, lazy. Right? This is our x-axis. We don't care about y-axis. You'll see. Well, we're going to later, but you'll see for now. So x0, v0, t0. x1, v1, t1. Okay? And this is a 10 degrees incline, and this is 50 meters. All right? Okay, so let's see, where do you want to call the, remember, we're thinking of just a 1-dimensional problem, so we're going to call that the origin. All right? Okay, so we're starting, usually you start at rest, right? You're seeing. So x0 equals v0 equals t0 equals 0. Awesome. Okay, now what's x1? So we had to figure out, we had to do all this trigonometry to do x1, right? So what's x1? Well, we know that the sine, remember, this is x0, so this is x1. So we got to know this distance, right? So now the sine of 10 degrees is opposite 50 meters divided by the hypotenuse, which is x1. So therefore, x1 equals 50 meters over sine of 10 degrees. And that is equal to 288 meters. 288 meters. Right? So x1 is 288 meters. Okay. v1, that's what we want. v1 is what we want. And T1, we don't know, right? Oh, sorry. We don't know T1. What else don't we know? We don't know A. We don't know A. All right, awesome. So that's our pictorial representation. We're all happy and wonderful, and it's great. Okay, we want to get the speed at the bottom. We don't have any time information. So you got to remember those 3 kinematic equations, right? 1-dimensional kinematics. So the first one has time, can't use that one. Second has time, can't use that one. Third one doesn't have time. Yeah, we're going to use it, right? So the third one is v1 squared equals v0 squared plus 2ax1, right? That's what it is, And then you say that and you go, oh man, I can't do it because I don't know A, right? I don't know A. Well, no kidding. That's what you do in chapter 6, right? I mean, All right. So you don't know A. How do you get A? By doing a force diagram. Oh, golly. So that's what you're going to be doing all this chapter. So just do it. Okay, so let's do it. All right, so, here's the skier. Here's that 10 degrees. All right, so what are the forces acting on the skier? Well, there's always going to be weight, right? So just get used to drawing the weight. There's always going to be weight. And what else is there? There's no friction. But wait a second, she's skiing down a hill, so it's normal. All right. So that's it. So let's tilt the axis. Might as well. We can always do it. So there's our y-axis, and here's the x-axis. And so here's Wx, and here's Wy. All right. Again, if that's 10, this is 10. So let's do it. Now, all we want is A, right? And A is this way, So, we can be lazy because do we need to do the y problem here? No, because the skier is not accelerating in this way, right? So the y problem is equilibrium. But the skier is accelerating this way, so the fx problem is not equilibrium. So let's forget about the y problem, let's just do the x problem. Why not? All right, so the sum of the x forces, which equals ma, right? Or max, but ax is the same thing as a, right? Okay, so what's the sum of the forces? Well, this is cool, right? The only x force is what? Wx. Well, what's Wx? It's W, well, okay, what's W? Mg, right? It's Mg, x, right? Which is Mg, what? What is it? Sine theta, right? Right? Sine 10. Sine 10. Now this is cool, because again, we talked about this before. A lot of people, when they see a Wx, they automatically think, it's cosine. Well, it's not. You got to analyze every problem individually. So we want the x component of the weight. That's sine theta. Okay? All right. Okay, there it is. So we have ma. So we have ma equals mg sine theta. So let's write it down. ma equals mg sine theta. We're going to solve for a. Divide out by the m. Divide out the m's. Divide. And we have a equals g sine theta. Or 10, sorry. 10. Okay. All right. And then plug it in, you get 1.7 meters per second squared. By the way, I don't remember what chapter, but somewhere along the line, I told you that when we had something coming down an incline with angle theta, that A was going to equal plus or minus g sine theta. I told you that. I told you we'd see why later. Well, now it's later. Okay, we just saw it, right? G sine theta. G sine theta. Okay. So now we're happy, because now we know A. So let's solve for V1. So therefore, V1 is square root V0 squared plus 2AX1 square root. Okay, what's V0? 0. We have 2A 1.7 meters per second squared. And what am I saying? X1, where's X1? 288. And plug that in. We get 31.3 meters per second. Okay. Now, is that reasonable? Well, I mean, it's really going fast, right? But I mean, it says frictionless, so it's reasonable, okay? All right. So, this is your typical one-dimensional problem for chapter 6. It looks like a kinematics problem, so you treat it like a kinematics problem. You do your pictorial representation and all this stuff that you did a long time ago, and you realize you need A. And how do you get A? By doing the force diagram, all right? And then you get A from the force diagram, then you stick it back in the kinematics and get the right answer. So like I say, this uses everything that we've used up to this point. All right, let's see. Okay, we are going to quit.